Cool. Thank you so much, all of you, for coming. We have more than 40 listeners, and we have Pavel here. So, thank you so much for making the time and joining us today. We really appreciate it. Um, it's an important part of the study group today. After the few weeks of introduction, this week we are starting the actual deep dive with live sessions into different parts of the execution and consensus layer. So today we are diving into the heart of the execution layer, to the EVM itself. And we have the one of the best experts to discuss this, Pavel, who is part of the Epsilon team of Ethereum Foundation, the team that is working on the EVM itself, doing the research and development, shaping the future of the execution environment in Ethereum. So one of the leading researchers on the topic, but also author of EVM1, a performant implementation in C++, which, like, I mean, if you implement EVM in C++, like, you must be the expert. Like, that's just incredible. So Pavel is the right person to give us a deep dive here. Yeah, and yeah, thanks again for being here, and the stage is yours. Yeah.
Okay, thank you for introduction. I'll try my best. So yeah, how as Mario mentioned, I mostly work on EVM at Ethereum Foundation. It has been around 10 years already that I've been doing this, and and yeah, one of the projects I work on, but it's not only me. There's a bigger team. The team at Ethereum Foundation that works on EVM research is called Epsilon, and we maintain one of the implementations in which is in C++ called EVM1. We also do some like API design for EVM integrations. And previously, we were even working on a project called EWASM, which was, I think, the idea to bring WebAssembly to Ethereum as the like kind of second execution engine. But it didn't actually happen in the end. I also work with Aragon Technologies, so the company that is behind the Aragon client, and I help mostly with EVM integration there. So they experimenting with EVM1 as the as the EVM implementation, and I'm just helping to make the integration rather smooth. Yes, that's about me, and I'll try to do um, explaining if there's anything to answer to. Okay. um, yes. So yeah, I'll try to explain some, like, say, from high level overview of Ethereum virtual machine to with going a bit into more details in some aspects. Um, so we start with explaining actually where this execution happens, know exactly how it happens, but like why it's there. And then we'll go from some overview of virtual machines in general to specifics of Ethereum virtual machine. And in the end, I'll try to kind of focus on some unique features that EVM has comparing to some other like virtual machines. And finally, I want to mention something that is potentially the kind of evolution of EVM, which is EVM object format. I thought that maybe it's kind of to better glue EVM as the component of Ethereum is to kind of explain what is executed and where it actually is and how it happened that some execution happens on blockchain. Um, I think that the two main concepts that are interesting here and important, which is transactions and state. And I think researchers and some developers like to think uh, about execution and in general evolution of blockchain as a some kind of transition function. So mostly uh, there is some like state of whatever the Ethereum blockchain represents, and there's a way to modify the state. So mostly we take a state as a mathematical object and apply some modifications to it, and we get like another state, which is kind of the same class of objects, but it has different internals. And this transition happens by mostly collecting transactions uh, and combining them into blocks. I kind of like to think that blocks are just kind of implementation detail why it happens. It's related more or less to consensus than the actual execution. But this unit of execution that actually initialize the any execution on blockchain modification to state is a transaction, and so it kind of allows you to modify what is recorded in a blockchain. And this Ethereum state seems kind of mysterious and seems complicated, but from at least from EVM perspective, it's actually a pretty simple thing. Maybe it's not a small one, but it's in the structure, it's actually not very complicated to understand once there. So the state of Ethereum, it's how EVM sees it. It's just a collection of accounts, and this collection means this some mapping. So the account have addresses which I uniquely identify them. So at the first level, we have some kind of map that assigns accounts to addresses. And the account itself is also not a very complicated object. It's just like 4 items. First one is the kind of specialized to Ethereum blockchain, which is the like amount of ETH the account holds. So it's specialized in the sense that this makes this ETH cryptocurrency something unique that it's kind of the currency of this specific blockchain. Then we have some number that is called nonce, and it has actually more than one purpose, but it's kind of like detail of some aspects which I don't think is super important. And finally, the account may have code, and this is exactly where the EVM comes in. So this code can be interpreted by EVM. And finally, this additional storage that the account can have, which is another map from keys to values. If you, what is the best kind of analogy? I think browsers have something. It's kind of like key value database with quite heavy restrictions. So the keys are up to 32 bytes, and values are also 32 bytes. So it's not like very generic, and sometimes you need to really hardly pack stuff into it. But yeah, I think browsers and JavaScript have something like IndexedDB. I think it's kind of similar. So it's kind of simple data structure that the code can access. And that's mostly it. How EVM actually sees the state of Ethereum. So it's all of these accounts. There is kind of the like second dimension here, which is related to commitments. So we need this state is also organized in a hash tree that allows you to kind of summarize what's in the state in the single hash, and also prove that some values are in the state. But this is actually not what EVM cares about. This is related to mostly the higher level. So we can skip this part. And there's one more aspect that is, I think, interesting to the state, that there's kind of two kinds of accounts. One is called EOA, which stands for externally owned account. And these are the accounts that people control mostly. So there's always some private key assigned to it, and the address is derivation of the public key. And whoever has the private key of such address is able to initialize a transaction to the blockchain. Um, and such accounts don't actually have code and don't actually have storage. So it's only the amount of ETH you have it on, and the nonce is actually related to this cryptographic private key and later to signature. But I won't really go into detail why it's there. And finally, the other type of accounts are contracts, which actually have a code and can access its own storage. It also uses the balance, so these contracts, the programs on the blockchain can also manipulate the balance of ETH by themselves. And this nonce number is also used for something, but it's also kind of a detail. But an important aspect of that is that the contract's are actually passive. So there's no way the contract can initiate a transaction. So it's always this externally owned account that has to do it. Otherwise, nothing will happen. Okay, so because that was the first section, I kind of warm me up. I wonder if there's any questions so far.
Hi, it's a bit slightly out of a bit out of context, but I'd like to understand if later on, if we have time to actually dive maybe directly into the the Aragon's code, and then just run through what we actually learned today, and then maybe highlight how Aragon. I know there has been like articles online that how Aragon actually differentiates itself in managing the state. So maybe those highlights in the code will actually be quite nice.
Um, I'm not sure I'm actually good the person to do that. So I quickly explain is that Aragon it's mostly written in Go, and there's some pieces that are written in C++, and I mostly work on like this C++ EVM. So I think it would be kind of probably much imprecise to describe the architecture of Aragon from my point of view. I'm not really very into deep about details. But maybe if that's interest of you, maybe you can ask some people from the team actually to give some overview later.
Nice. Thank you. Thank you very much. Okay. Thank you.
Thanks. Okay. So now, quick overview of virtual machines. I think there are two actually conflicting terms under the virtual machine. one is this all this like cloud and stuff, which this is exactly what we don't care about so much. So what we mean by virtual machine in this context is, I think it's sometimes called process or application virtual machine. And if you're familiar with anything like Java, .NET, C Sharp, WebAssembly as well, these are all like different kind of process virtual machines. Um, and this concept, this is kind of like computer science evolution of programming languages mostly. And like classic programming languages just target, well, they have compilers and they target different hardware and different architectures. So in some sense, if you have different programming languages um, and multiple hardware you would like to this programming language to be able to run on, you need to kind of implement this hardware backend for each compiler. And as we kind of IT people notice, this a way to add one more layer to this thing, and then you can create some intermediate representation. And that's like different levels of how this can be done. But I think Java was kind of the maybe the most popular product that actually emphasized this, that you can you can just have some intermediate layer that will handle will kind of abstract the hardware of the compiler. So instead of targeting multiple hardware by multiple compilers, all of them can target single single machine that is have some virtual set of instructions. That's not exactly what runs on the hardware, but how to actually execute this virtual machine on the hardware is the virtual machine job to solve, not the compiler job. And classically, that's what's usually people describe first when they try to say something about specific virtual machine is if it's stack based and if it's register based. These are kind of like basic concepts how you can organize your virtual machine, and all of them have kind of infinite resources. It's just the resources are organized into a different structures. So a stack-based virtual machine just have a stack, which is, well, it's a memory when you can only manipulate like the top items, and it's kind of has infinite number of items you can store, but you cannot really access most of them all the time. The register-based virtual machine have some numbered, fixed numbered values that you can manipulate values of. Mostly, the the stack-based virtual machines are a bit easier to implement and to work with. It's mostly because the encoding of its instructions usually fits into a single byte, and that's where the bytecode term comes from. So it's this intermediate language that virtual machine can execute on, which has instructions encoded like a single byte. For register-based virtual machines, you mostly need to encode which are the input registers and when the result, in which register the result will end up. It's also not specific to the technology, to the like set of languages. For example, there's multiple Java virtual machine implementations, and some of them are stack-based, some of them are actually register-based. So I think there's not strict rule, which like if a language actually has like single version of it. For EVM, we also in the stack-based category. like quick overview, how does it work? So for a stack-based virtual machine, if you have add instruction, it usually means that it takes two top items from the stack, and this SP marks the top of the stack. It adds the values and then put a single value on the stack back. So in this case, 20 plus 7 gives you the top item of the stack of 27. In case of register example, in this picture, the add instruction has to encode which registers are in the input, in this case R1 and R2, and the result will go to the R3 register. Okay, so that was quick intro to the virtual machines concept in general, but now let's take a look on how Ethereum version of that works. So as I mentioned, it's also stack based and it uses bytecode. So every instruction, it's 1 byte, more or less. There's some aspects of it which kind of differs, but at least the opcode that encodes what's going on is a single byte. And the EVM has significantly big stack items, so it's more than the native hardware actually supports. So there's some kind of level of emulation of arithmetic. There's no any validation, so whatever the bytecode is provided to it, it will do some execution of it, potentially returning some errors, but it's in some sense it will produce deterministic results on any sequence of bytes it sees. It has also multiple different kind of memories inside. I'll try to explain later, and some exotic features. And the kind of original goals from EVM design from 10 years ago with simplicity, total determinism, compact code size, and some specialization to blockchain execution needs. So this specialization actually is the reason for having this bigger than native values inside EVM. So it uses 256-bit values. So that's more or less 4 times the size of the native hardware supported. So we need to emulate that in software. And this, I think one of the reasons that it came out this way is that blockchains heavily rely on secure hash functions. And the hash functions usually have 256 bits of the output. There are some variations, but that was the most common at the time. So using this bigger values in EVM kind of makes the output of the hash function also natural. It's a value that is actually naturally represented inside EVM. And that was one of the kind of inputs to design that make it this way. Okay, so now how it actually operates. So most of the implementations of EVM, if not all of them, publicly known, are actually interpreters. So there's some kind of loop that goes over every instruction and tries to execute what's encoded in the instruction. But there's a bit more to that, and I think that's usually overlooked on the first side, that EVM actually does a bit more than people can imagine in terms of execution efficiency. What I mean by that is that there's more steps, more kind of work the EVM has to do before it actually does something what the program wants it to do. So it has to fetch the instruction for sure. That's basic. But because the bytecode can be anything, it also has to check if the next instruction even exists. So that's another thing that the naive VM implementation has to take account of. And because there's no validation step in EVM, it also has some pre-checks, meaning that the currently fetched instruction may cause some failures in the execution. For example, there might be not enough items on the stack to operate on, or or the result of the instruction can overflow the limit of the EVM stack. So all this check has to be done before execution. And there is one more thing which is related to the gas cost. So gas is kind of one of the unique features of EVM, and I will go back to it a bit later. But also, EVM also has to check. First, it has to compute the cost of the execution of an instruction, and then check if it actually doesn't go above the gas limit that has been provided. And only after this, it can actually start executing what the instruction says. So this actually contributes to inefficiency of the EVM implementations. So these are numbers more or less for EVM1. And if you go a bit more naive approach, so it can be even worse. So yeah, so there's definitely some efficiency overhead related to the kind of simplicity of EVM. And I didn't actually count it how many instructions EVM has, but there are some groups of instructions that we can put them into categories. There are some something basic you would expect from it, some arithmetic. There's also some work on modular arithmetic and bit manipulation and some comparisons between values and so on. There's some control flow instructions and memory access. But this kind of more on the kind of exotic side of thing. There's a lot of instructions that just bring some external information or data from the blockchain environment. So something that you can query some information about the current transaction on the current block. And finally, you can access storage with specific instructions. So this kind of private data or data structure that each account has. So whatever the code, on whatever account the code is, it can access its private data structure. It's a private to EVM, but it's also publicly visible from anyone else who is observing the blockchain. But at least the code controls the updates to this data structure by its own, and nobody can do it for it. And finally, there are some ways of interacting with the other accounts. So one contract account with a code can interact with some other code in some other address, or even create new contracts with code. And finally, there is a special instruction that computes secure hash function of Keccak 256. So this is more or less to give you overview what can you expect there. Okay, so I would like to focus on two aspects now that is a bit more unique to EVM, but if there are any questions so far, I'm happy to take it then.
Hi, this is Kenneth. I understand that you mentioned that we work on the 256-bit instructions. But I do see online that there is actually a 384-bit I guess a research on 384-bit implementation for the easier computation for elliptic curve cryptographies, in particular the BLS 12381 signature. So I want to check if there are any EVMs out there that are actually making use of these three. I guess it's called EVM 384.
Well, I think what you mean is that there are some like cryptographic, let's say, kind of primitives that use values other than 256. And yeah, 254 is kind of also used sometimes. So we have some cryptographic primitives also kind of available to EVM that uses elliptic curve of this size. But I think that mostly affects the only like very narrow aspect of arithmetic, which is related to finite fields and so on. So this is not exactly how EVM works. But yeah, in some sense, the abstraction of EVM gives you this power of two kind of limit. So all the values are from 0 to 2 to the power 256 minus 1. So it means it not exactly fits into this cryptographic world very nicely. One of the issues comes in a ZK implementations of EVM. Maybe that's what you also refer to. That kind of natively has this a bit lower limit of arithmetic, which is related to what I said, finite fields, and then they have to emulate the kind of the standard EVM behavior somehow. So EVM always has the same value size in different blockchains. But yeah, sometimes it's not natural value. And on some level, this ZK EVMs try to mitigate that by providing different programming languages where the natural value is actually different than EVM natural value.
I see. Thank you very much. That clarifies it.
Perfect. Yeah, I had a question. You mentioned earlier that mostly all operations are 1-bit length. So what does it mean for, like, for example, the push operation to be greater than 1 byte? And does that mean that it overflows into the next location in the stack? Could you?
Yeah, understand. So like push instruction kind of breaks this abstraction, but mostly how EVM works, it always checks the next byte to know what to do with it. and usually the instructions are just 1 byte, which means it can start executing after that. The push instructions are kind of different in a sense. They will actually have some payload after this single byte. That means that it describes the instruction. So I think this analogy of the bytecode is kind of not really strong. Maybe this abstraction, and this is also case not only for EVM but for any other stack-based VMs, that it's not necessarily like single byte that describes everything. Sometimes there are like follow-up bytes that you need to also process to execute the instruction. In this like basic EVM, there's only push instructions that has this property that there's like follow-up bytes that you need to actually load. So what the push instruction does for people that don't know, it just kind of puts a constant value on the stack. Constant in the sense it's encoded in the code, so it cannot be changed during execution, and it can be value from zeros to whatever up to 32 bytes, the size of the natural value of VM. And that's kind of simple what it does. But the encoding of the value to be pushed on the stack is actually in the same code, so it follows after the first byte that describes the instruction. It's a push instruction, but also describes the length of the following bytes to read. So after you finish push instruction execution, you need to read another byte to get the next instruction. So kind of execution of the instruction itself has to handle this payload bytes as well. So the next time interpreter loops from the start, it can safely read 1 byte and then decode it as the next instruction. So so this bytecode, it's not precisely describing how the actual code is structured, but it's not specific to EVM actually.
Awesome, thanks.
Yeah, so I was just very curious about why EVM is fundamentally interpreted and not compiled. Given that we have something like just-in-time compilation or like ahead-of-time compilation, maybe WebAssembly-based execution as well, which can significantly improve the performance of VMs, right? Maybe by optimizing instructions or like doing some redundant computations easily. So like, why has Ethereum not adopted these yet, and why specifically interpreted? So that's what I was curious about.
Yes, I think there's multiple answers to it, but I think that the easiest is just it's actually a bit hard. So EVM was actually not designed to be just in time compiled and to be actually translated to anything else. And it was at the beginning it was so annoying to do it, because one of the first projects I had was actually to write a just in time compiler for EVM. Was that it was almost impossible because of the control flow that instructions that EVM has, and I will talk about it later. Actually, it was so bad that you cannot predict where the with this control flow instruction will jump to if they have to. So in some way, the EVM is very simple, but it has kind of unconstrained control flow instructions, which are not really compatible with translation and compilation, because it's just like too kind of weird. and that was the kind of the issues. So on the contrary, WebAssembly was actually designed in this compilation in mind. It's actually the default mode of execution in browsers currently, and that was the main kind of goals of the WebAssembly. And with the EVM, it wasn't, and we actually made it unnecessarily difficult to do so. And we also have some constraints on the kind of on the level that we expect not properly behaving inputs, right? Because everyone can deploy the bytecode on a blockchain. It's kind of permissionless and there's no validation. So you kind of have to be prepared for really awkward edge cases if your compilation pipeline is too complicated. But we try to fix that, and I also come to this topic if I have time.
Yep,
Yeah, but
thanks. Got it.
current situation is that's mostly interpreters. Okay,
Yeah,
so
got it.
let me try to move on. So we still have time in the end. So I want to talk about two more kind of unique features of EVM. One is internal calls. So this is a way to when the contracts, which I usually think about as a kind of so I think I like the analogy that the contracts are mostly sitting there as a kind of so you can imagine that blockchain is a kind of file system and you have a programs in this file system. So there's some files with a code in it. And then can come a user and invoke one of these programs. And then this program can actually interact with other programs on its own. So this is kind of unique feature in the sense usually programming languages or like virtual machines don't allow it very freely. You can imagine, I don't know, if you program in Python, you can definitely call other files and other functions from other modules, but executing a different process is usually something slightly more complicated. So you need to load something from a standard library. When you execute a process, you need to specify a lot of parameters to execute. You need to specify how the output should come to you, like is it like standard output, is it like error output, like both of them, how to, yeah, what would happen if it crashes, and a lot of that. So if you work with like multi-process applications, actually it's actually kind of advanced thing. In EVM, it's relatively easy. So it's still complicated because all of these aspects you need to take care of, but there are dedicated instructions that just almost like execute other contracts in kind of isolated container of a process. So they actually cannot really do much to you back. So they have different memory. They have almost like a new instance of EVM. So the stack is different, the memory is different, the storage is private, and you cannot see what they're doing. And then it can only return some data to you in the end. So EVM has multiple call instructions. They are differ by some like details. So the call is kind of the most, say, the basic one. It's hard to tell it's basic, but this is kind of like the basic in a sense. It executes other contract as you would imagine it to do. And this, I think, some number of parameters you can pass it to. So definitely you can specify whatever address you want to execute. You can also specify how much gas. So gas is this kind of resource that limits the execution. So we never actually go into some infinite execution. So not only the transaction sender can specify how much the transaction can use, but then during this chain of internal calls, you can also decide how much gas you will pass to the callee, and so there's control over that. Although we're working on a way to actually remove this control, but potentially in the future, you can also send some if with the call, and then the contract you're sending it to can react to it somehow. So you can also record how much if you send, or do something if you send non-zero value, and many aspects of that kind of makes this if cryptocurrency special for Ethereum, because it has like direct way of sending it to different places in EVM. And then finally you can pass some arbitrary data to the callee, and then it can do something else. And there's also like multiple other properties you can specify. Like for example, the static call I mentioned at the top is that it works as execute other process, but it also restrict this process to do any modification to the Ethereum state. So it can also give you some information back, but cannot modify anything in the Ethereum. And as a result, you get another set of arbitrary data, whatever the contract decided to send you back, and also whatever the gas remained after the execution. So it can happen that the contract you called will not use all of the resources you provided to him. So whatever is remained, it will go back to you, and then you can use it to some other computations or processing. Yeah, so this is, I think, one of the most complicated aspects of EVM, as well for the implementation, which does a lot of details to and a lot of different pre-checks and post-checks that happens around this. But still, this is really powerful feature that makes this interaction between accounts and the contracts relatively straightforward. And there are also instructions that instead of calling some existing account, can create a new account with a new code, and you can also decide how the new account how it's supposed to be created, and specify the way of creation of account also as a EVM program. So it's mostly it works closely to some kind of basic compiler that creates new items in the state. And as I mentioned already, there's multiple memories EVM has. So we mentioned the stack where this like basic items reside on, and you can the instructions actually manipulate the values on the stack. But there's also this more free memory. So it's closer to this classic CPU design when it's like byte addressable infinite in this case area where you can put arbitrary values in some unrestricted way. The only restriction is that accessing this costs you some gas, and the size of memory you're using also costs you some gas. So conceptually, this is infinite memory, but you are limited by the gas resource, how much you can access it. And finally, the two another memory buffers that related to the input data to the call and accessing the data returned from previous calls. And these are kind of read-only memories. But because there are different buffers from the main EVM memory, it means that has to be some instructions to access these different buffers and also to move data between these different buffers. So that's kind of because EVM has these multiple memories. It means there's also like specialized instructions that moves data between different kind of buffers. And finally, the storage, which is it's not like a continuous memory. It's just a key value map, but there's also dedicated instructions to manipulate these. And this is like readable memory, so you can modify the values there. And gives you some like basic overview related to this call data, return data buffers. They are related to the calls. So if you have on the left side the call instruction that targets some other contract, the amount of the input of the call instruction becomes a read-only buffer on the callee side, where it can access and it's called call data. So there are special instructions to access this, but you cannot modify it. And finally, after the second contract finishes execution, it can also return some data back to the caller, and then this data called return data is also read only, but this time for the caller. So it can access it, read whatever has been returned, but also cannot modify it. And to move data between these buffers, you need another set of instructions. And whatever actually comes from the transaction itself, if you are kind of more or less familiar with the transaction structure, then you can also put arbitrary data in the transaction. This is what the top level execution will see as the call data as well. Okay, so that was more or less about how calls work, and now the second unique thing of EVM is this famous gas. So the gas has been kind of natively introduced in EVM as a way of limiting the execution time. So conceptually, it works as something you subtract values from. So you have some, let's say, EVM for execution has some gas counter that is initialized to the limit the transaction provided, and then every instruction subtracts some value from it, and if it goes to 0, it means the execution has run out of the resource to perform computation, and then the execution terminates, and it terminates with a failure. So whatever has been done so far, any modifications to the state, mostly, I mean, the Ethereum state matters the most. So any modification to the state is reverted, and any other kind of observable effects are also reverted up to the cache warm-ups and logs. So there are features that not directly reflected in the state modification, but still something you can see, for example, from the application interface. and this kind of playing with the gas happens on multiple levels. So when you send a transaction, you can specify the limit of the gas, and by this also the cost of the transaction is computed. Usually wallets do this, so they kind of try to estimate how much gas you will actually need to successfully execute a transaction, and then it puts a value in the transaction for the user mostly, and based on this, it's also the maximum cost of the transaction is computed. But as I mentioned already, when you go into internal cost level, that also you can kind of control the amount of resources you provide to the colleagues. And finally, the transactions are packed into blocks, and the block also has some limit of the gas. So that's maybe you actually also heard of, but this is this block gas limit that is sometimes discussed on social media, that we should increase it or decrease it or whatever. So this is because there's also value that the block cannot exceed in terms of EVM computation. This kind of like a second dimension of the gas. So we have like single unit to also reflect the cost of making changes to the state. So it's not about computation, it's about to recording the database changes that happens. And it's actually reflected in the same unit, which has some like kind of bad properties because these costs are not really very well correlated. So it's mostly asking a question, if computing some addition, how to compare computing some addition of two numbers and storing 32 bytes of data in blockchain forever, how to actually reflect these two kind of different dimensions into a single unit. I think we struggle a bit with this. So the idea is to actually split this cost into multi-dimensional pricing, but so far this all reflected in a single unit. And most of basic instructions have some constant cost. So for example, from the current spec, pushing new constant value with the push instruction on the EVM stack cost 3 units of gas. And sometimes instructions have a bit more complicated formula. So example would be the exponent instruction, which computes the exponent of two values. And the cost of it depends of the length of the exponent actually, because there is not like constant time implementation of that. It does more work if the exponent is bigger. So the computation is kind of reflecting, the gas cost reflects also the values of the arguments coming to the instruction. So it can be more complicated. Also, the size of memory is, so if during execution you actually use more EVM memory, you also pay for the expansion of the memory. And finally, something like accessing Ethereum state has a bit more complicated prices because it tries to compensate from reading cold and warm data from the database. So this gets complicated. So what I wanted to say, it's for some pieces of EVM, this is like straightforward, simple value lookup. For some other things, it's actually complicated thing to compute. Sometimes it actually very much affect effectiveness of EVM execution because you may actually spend more time computing the cost of the instruction than actually executing the instruction. Okay, and then I have, I think, two examples of instructions to maybe kind of summarize what has been said so far. So add instruction has the opcode value of 1. So opcode is this byte that uniquely identifies the instruction in the bytecode. And as you can imagine, it requires at least two items to be on the stack. So if there's less than that, the EVM will also terminate with a failure. But if everything is good, we have at least two items on the stack. What conceptually this instruction does, it takes this value from the stack, it adds arithmetically them together. And because there are 256 bits values, it means it will add them, but with this wrapping at the 2 to the power 256 value. So, well, it works as a wrapped addition. And this result is pushed back on the stack. So mostly two values are replaced with one new value. And the cost of that is also 3. Data copy instruction. So this is instruction to to get some range of data from this call data, which is read only, and it comes from transaction or some like higher level internal call. And it copies this to this read and write accessible EVM memory. And it takes three items from the stack. The top one is the offset of the call data you're interested in. The second one is the offset of the memory you wanted to copy it to. And finally, this number of bytes you want to copy. And so first of all, you need to make sure, EVM has to make sure that these three items are actually on the stack. There's also some edge cases related to what happens it goes out of the actual physical call data that is available. And what usually EVM does in this case, it specifically does it in this case, but there are some kind of other memories which usually behaves the same way. It's kind of fakes the user as there's like infinite number of 0 bytes after the actually physical ones. So mostly it will pad these different overflows with zeros. So that's not a failure. It's actually deterministic behavior of EVM. And well, that's so mostly what it does, the instruction copies this range of bytes from one place to the other. And the cost is actually proportional to the size of the copy. So so like base cost is 3, and there's like another 3 for every 32 chunk of 32 byte chunk of data. So we need to compute that as well. And it's like rounded up. So rounded up is actually difficult to compute than rounded down. So we also need to spend some time of computing this. And finally, there's some additional costs to expanding EVM memory. So if it has been used in this range already, that's fine. There's no additional cost. But if you actually copying this data to some EVM memory that hasn't been used before, you also have to pay for the expansion of this memory. And this is actually quadratic cost. Okay. So, how are you doing so far?
I read somewhere, yeah, I read somewhere that like you just told that the instructions are 1 byte. So I read that only the top 16 elements of the stack can be accessed for computation. So like, how does it work then?
I'm not sure I fully got the question. So I mean, how it happened that, for example, add instruction is 1 byte, how it knows what to compute?
Yes, like I read that uh, since it's 1 byte, so 8 bits, 4 bits for the function and 4 bits for the position. So since there are only 4 bits for the position, we can't access more than 16 elements.
Yeah, so this is kind of the basic kind of design of the stack virtual machine. So you actually don't specify the position. The position is implicit, and it's always like the first and the second item on the stack. So before you do addition, you as a kind of compiler or like programmer or whatever, you have to make sure that the values you want to add are actually on the top of the stack, right? So if they are there, you're fine, and you can add them, and then the result will also be on the top of the stack. So that's why you don't have to encode the positions of the values you want to add in the instruction. So it's enough to have single byte that says this is addition, and it means that we'll add the top one and the second to the top items. And then, so it kind of looks that we save a lot of code size this way, but it's actually not this nice. Because if the values you want to add are not on the top of the stack, then you need to kind of move it there somehow, right? And there are additional instructions that actually are specific designed for that. So so there's like dupe instruction that you can specify which instruction in the range of 16 you want to duplicate on the top of the stack. So you can use this. So your access size is only like 16 elements. And there's also a swap instruction, which is similar, but it will not duplicate. It will just move the top item of the stack to the and swap it with the value that you specify. It also has more or less the 16 items range. So kind of in general, if you look on the compiler generated code, or even if you would write it by hand, you will notice there's a lot of this dupe and swap instruction actually happening. So somehow you can think it's kind of a faking that the proper encoding. So whatever you see some like core computation instruction, like addition, for example, they usually preceded by like 2 different dupe instructions. So mostly you're actually encoding of doing addition of 2 variables is actually 3 instructions. First, you need to duplicate one of these 16 top items. Then you likely need to duplicate another one. And then finally, your result will be on the top of the stack. And this is also this like limit of 16 is also this famous solidity stack to deep error. It's like when you actually the compiler cannot figure out easy way to access some value that is on EVM stack, it will report an error. There's definitely some ways to mitigate that, but if you ever heard about this issue, it comes from this limitation of EVM.
Okay, sure. Just one question more. So, as I said, that the EVM architecture was designed for 256 because of the most used hash functions, which were 256 bits. So, if we were to move to a higher number of bits hash function or crypto or any other, so we would have to change the architecture also.
No, I don't think so. So I think this is nice abstraction that EVM has. If it's practical, that's kind of different question. But I imagine if we want to change the well, first of all, we'll not probably replace the current hash functions with a new hash functions, because replacing means it will break existing code. So usually how EVM evolution works and how the upgrade to EVM happens, we kind of really pay attention to backwards compatibility. So these hash functions will stay where they are. And some of them, like one of them is actually instruction EVM, but there are two other hash functions relatively easily available to EVM, but they are not implemented as the instruction. They are implemented as this pre-compiled contract, so kind of fake contract that has no code but pretends to have some code, and this code actually computes the secure hash functions. I think this is like another topic about this thing, but yeah, I think I will not really have time to explain this currently. But mostly we work as a kind of we mostly work by extending EVM. So if this new hash function needed, and if it's even bigger than that, I would need to figure out how to actually fit it in. But it can be different ways of doing so. It can return just like two stack items, for example. We don't have any instruction that like practically does it currently, but I don't see this as impossible. You can also work with memory. So you can, even if you want new hash function that is instruction, you can define it in a way that it will not output the result of the hash function on the EVM stack, but you can, for example, put it in at the memory index that you specify. So if it needs like 50 bytes, for example, of the output, then you can specify the index in memory and it will write this 50 bytes at this index, and then you have to kind of process it in EVM in some way, but it's up to the kind of user how to do that. So there are definitely ways of doing so. Something that will not kind of need to redesign the basic kind of design properties of current EVM. Okay. Yes. Okay. So I think this is the final topic, but it's kind of also unlimited in some way. So as I mentioned, EVM kind of doesn't have any validation step, and it just executes whatever bytes are there, and there's no restrictions what you can actually put in a contract code. And I think that's simple, but it has a lot of bad properties, and we try to fix that in the EVM upgrades in some future. Okay, so this goes back to, not goes back. So because of this missing validation thing of EVM bytecode, I think it has accumulated a lot of problems during this 10 years, and there's one of the attempts to fix that, which is called EVM object format. And this is something I've been working on for some years right now. And it's kind of borrows from WebAssembly experiments as well, and some other designs for virtual machines and so on. So what we actually want to do with this, it's kind of to structure the bytecode in some way that it's easier to execute, but it's also easier to work with and also to analyze, and it has some other properties. But this is done by actually introducing this validation step. So mostly on the practical side is that we will define what a valid bytecode means. And when you try to deploy a new contract, it has to pass these validation rules implemented in Ethereum nodes. And this means that whatever is deployed on blockchain and whatever the code is in the Ethereum state we will know that it's already valid, so we can actually extract this information later on during execution. And some nice quote I recently heard about it is that it prevents bad behavior with complexity, and this complexity is the validation. And some kind of visualization of that is that, okay, so because it's a new thing, so we started call the old EVM as a legacy EVM, but it's legacy in the sense that will introduce something new side by side. It doesn't mean it will not work. So in this current EVM, not to emphasize its worth, like everything is kind of mixed together in the bytecode. So we have some data there, which is not really visible. So you can think that the push instruction has this payload of bytes. You can think about it, the data, but usually what the compilers do, it will put something that is executable at the front, but then in the end, there's some bytes that actually never meant to be executed. Although for the EVM, it's actually really difficult to distinguish these two. So whatever it does, some analysis of it, it has analyzed everything, and it can't really know that these bytes are never executed because it's like fundamentally impossible to decide if for any program you can actually reach some instruction somewhere or not. So it's all mixed together. There's some like data that the contract will use later as like the data section, but there's also like metadata that Solidity puts in to identify the source code on blockchain later, but is actually never ever meant to be read by EVM and so on. And so what this EVM object format tries to do on this like basic level is to just clean it up a bit. So we want to put some like metadata information up front about the structure of the later code. So we specifically want to split the code and the data into separate sections, and we want to put a version so like we can upgrade EVM more easily and guarantee backwards compatibility and so on. It's actually supposed to be like basic stuff, but there's a lot of details to figure out. To not to overcomplicate it mostly. I will not go into detail how exactly this is done, and because it might be like probably idea for a different topic, but let's skim over it for now. But what are the proper like the benefits of that? First of all, during validation, we can do some checks that would normally do on runtime. So we can guarantee that if an instruction needs 2 arguments on the stack, these 2 arguments on the stack will actually be there forever, whenever like code path the execution will take. And it means that during execution, we actually don't have to check these. So they are kind of guaranteed by validation. So whatever we load the code from account for execution, we can actually eliminate these checks at runtime. So it improves the efficiency of the EVM execution a bit. It's not like substantial, like number of times improvement, but I think it gives like between like 10 to 15 percent of speed up. Okay, and finally, it also modifies how control flow works in EVM, and this directly contributes to this ability to translate EVM bytecode into some other representation. So it kind of goes back to the question, why don't we have JIT compilers for EVM? Well, because the control flow in the current EVM is pretty bad to reason about, and it's difficult to translate it to some other forms. But with this modified thing, you can actually do it relatively easily. And I wanted to describe it as a kind of comparison what we currently have and what the new format potentially will have. but I'm not sure we can actually squeeze it into 5 minutes. So I'm not sure it's worth to actually go into this right now, unless you want to spend a bit more time on it today, or we can even schedule some other thing to talk about it. Well, it's mostly question to Mario, I think. Okay. Yeah. I can skim over it. Yeah. Okay. So let's try to do that. So mostly control flow in current EVM is done by 2 jump instructions. They differ mostly by like conditional and unconditional. So this conditional version just takes another argument and checks if it's 0. If it's 0, it will not jump to the target. If it's not 0, it will jump to the target. So that's the difference. From the structure of the program, there's actually no difference. But the problem is that it's hard to figure out where the jump will go to, because the jump target is also dynamic argument of the of the jump. So it's also taken from the EVM stack. So this like dynamic value, you cannot predict what it will be, and that makes it really difficult to reason about the control, like static control flow of the program. So we call it like dynamic jumps because of that. And this is like kind of overview of these like abilities, how different like intermediate representations and assemblers actually handle that. And mostly what I wanted to show here is that for EVM is just like single way of doing all of these different things. And that's why it's actually hard to, for example, translate EVM to LLVM IR, because it actually don't fit really into this restrictive structure of the other representations. Yeah, so we only have one way of doing jumps, while anyone else has like a more sophisticated ways. So it's because of that, it's hard to translate generic but really kind of too powerful thing to this more restricted form. So how like EVM object format tries to fix that is mostly replacing this dynamic jump with static jump. So we want to have new kind of instructions that has fixed target of the jump. So we know during analysis and validation where the jump will go to. And it actually works pretty well in most of the cases. And if you analyze the Solidity programs, you will notice that all the conditional jumps are actually static because there's a push instruction there before them. But it's for this, having only static jumps make implementation of functions in the contract really difficult. So that's why we also have dedicated set of instructions to implement functions. So it kind of fills the gap that was missing from the beginning to match the other representations. Oh, that's all of that. So if I go a bit to here, we kind of also try to fill the other categories with the dedicated instructions. And this allows you to analyze the control flow of the contracts pretty easily and translate them to other representations. Okay, so that was it about the control flow, more or less.
So now quickly, before we wrap up, yeah, we have a question from Prince Raj. Yeah, Raj, do you have a question?
Yeah, yeah. I have question related to the EOF. So in EIP 7620, there is idea to depreciate all old create and create to instructions. So how it will affect the current deployed contracts, like any factory contracts or some other contracts who is using the create to?
Okay, so I'm not really super and fully remember the EIP numbers, but you mean there's like create and it's potentially core instructions are deprecated, right?
Depreciated, yeah.
Yeah. So it's not like the okay. So on the first part of the answer is that we want to replace these instructions with the new instructions. So it's kind of the similar story as with the jumps. So we also kind of disallow to use the old jump instructions, and we provide the new ways of doing so. And it's the similar story for interacting with other contracts. What exactly is changed, I think I will just leave it for now. But they conceptually, the new instructions conceptually work the same as the previous ones. We just adding some small limitations to them. And sometimes we just clean it up because some of the features of the current instructions are actually also kind of replaced with a new way. So, so there will be replacements on the instruction level, right? So there'll be new instructions to do the same thing. Secondly, how this legacy EVM interacts with the EOF and the other way. So they will kind of coexist on the same blockchain, let's say. So there will be still the EVM, and there's a way to distinguish which bytecode is legacy and which bytecode is the EOF. And whatever the execution comes to the account, and then you will read the code of this account. You need to figure out. I mean, the EVM, let's say, as a broader component, we'll figure out, okay, this is legacy code, so I need to use the old EVM to execute it. Oh, this is new EOF version, whatever, and I need this kind of way of executing it. So it will figure it out by the version, let's say, and you can conceptually think that the legacy EVM also has a version, but implicitly. So it will know how to execute it, and this is purely for like backwards compatibility. So we cannot like modify the existing code. It will behave as it is. So we provide a kind of new site EVM in some way to deploy new contracts in a new way and potentially a kind of better way, and hopefully the adoption will catch up with this. But still, whatever the bytecode is a new form and the old form, they more or less will be able to interact in the same way the current contracts can interact with. There's like small details that are also limited related to delegate calls, which are kind of special kind of calls which execute code of different accounts, but in the context of the current account. And yeah, that's it's quite complicated, and yeah, and there's some restriction on this. But besides that, all these different bytecodes, new versions, old versions, can interact with each other as they were. Also, if the old legacy code has create instructions to span new contracts, that also will work, and that will create new legacy contracts. So this legacy contract will be created probably forever, at least for Ethereum mainnet. And the same way, the EOF contracts will be able to create more EOF contracts, right? And so, yeah, so that's kind of separation on some levels, but on interaction levels, it remains the same as it was.
Thank you, Pawel. And one more question related to EOF itself. As we know that, right, if we want to fetch the 16 more than the 16 items from the stack, then it will show you the stack too deep. Then how we are solving that in the EOF? Exactly how the things working behind the scene?
This is actually not like ultimately like super clever fix. It's just this. There are kind of new instructions that allows you to access deeper in the stack. So they're kind of
Up to
equivalent of
1024. Up to
up
1024.
to no, up to 256 because that number
Okay.
fits into single byte. So not the full stack access, but like quarter of the stack access directly. And this is simply implemented by having new instruction that has like one opcode and the next byte after the opcode says like which item of the stack to access, right? So there's like dupe instruction equivalent, there's like swap instruction equivalent, and there's one more that is called exchange. So it's kind of like generic, more generic swap version when you don't have to swap some some deep value with the top value. You can also swap two deep values with each other. So that's not really clever fix. It's kind of the same thing, but this is this is kind of where the validation also helps with, because we cannot actually introduce such instructions to legacy EVM. And this is reason because of this no validation. It means we cannot introduce this like 2-byte instructions into legacy EVM. The legacy EVM knows about push instructions, that they have like follow-up bytes that have some special meaning. But introducing new instructions can potentially break existing contracts that has this property that it's not single byte. And that's why introducing this like more power for dupe and swap instruction took so much time, and because it was actually not possible in this legacy VM design.
Great. Yeah. Thank you. Thank you so much.
So much
Oh,
for
I
attending.
still I think I had
Yeah.
most of the content I wanted. Um, so, but if we want to plan next session, I think I can next time can be a bit more lighter on the content, and we can maybe have more time on the questions. But yeah,
Yeah, I think this was a
thanks
great
everyone
time.
for attending anyway.
Yeah, awesome. Yeah, thank you so much, Pavel. Really appreciate it. I think it was a really great lecture, great slides with a lot of resources that people can study. I think we can take some time to study the resources and just maybe rewatch the PowerPoint recording, and then maybe we do some AMA or something later on. But for now, you're off the hook, Pavel. I mean, thank you so much. It was really great. Yeah,
Yeah, it was a
awesome,
pleasure. Thank you.
awesome. Really appreciate it. And yeah, have a great day, everyone.